All right, guys, today we're going to pick up where we left off, or where you should have left off before break. There were a number of you that did not do the assignments from before break. Those are still posted on Schoology, so please, I encourage you to go back. At some point, we will have some sort of an assessment. I'm not sure exactly how that's going to look yet, but that'll cover the last two assignments that we did prior to spring break. I hope you guys are all doing well. I know this is weird, but unfortunately, I think this is going to be our normal for the next couple weeks, if not longer. So again, you've just got to do your part and keep up on your end with the videos. If you've got questions, email me, and we'll go from there. All right, so in the last lesson, you were taking a look at some words, some descriptions, some equations, some graphs, and some tables, things that we've been looking at back when we were in school. And you had to compare the speed of the cars and which car started behind the starting line, which one started ahead of the starting line. And those cars had 2 or 5 different equations that you had to look at. So there's one of the equations, y equals 1/2 x plus 10. There was one that was y equals 4/3 x. There was one that was y equals 3/2 x plus 1. There was one that was just y equals 17. And then the last one was y equals 5/4 x plus 5. Okay, so we were looking at those 3 equations, and if you notice, those are in the those equations are in the form y equals mx plus b. Okay, we haven't talked a ton about that form, but really what y equals mx plus b form is just our y equals slope times x plus the y-intercept. Okay, so we've used that one many times. So in reality, the m is the slope, and the b in y equals mx plus b is your y-intercept. So m is just your slope, and b is your y-intercept. All right, so the first question, if you look at number 1, says, which part of the equation represents the speed of the car? Okay, so the speed of the car is what's constantly changing. So each of these with the x, those are all your speeds. So in the first case, 1/2 is the speed. In the second case, 4/3 is the speed, 3/2. This one we can really write as y equals 0x plus 17. So if you did the 28-1's lesson, this one wouldn't run. It was basically a car that started 17 miles ahead, or 17 inches ahead of the starting line, but then it wouldn't start. So it never changed. You never added anything to that 17. It stayed at 17 the whole time. So the part of the equation that represents the speed of the car is the slope. And then it says, how is the speed represented on a graph? Well, we know that speed on the graph is that change in y over change in x. And it's also the slant of the line, right? So we can say that if you look at the graph, it's how far that line is slanted. Oops, not slant of the line, not slant of the graph. Okay, if you look at your table, we talked about slope is the change in y over the change in x, and that's something that we've used quite a bit over the past couple weeks or months even. And then how do we know which car is going the fastest? Okay, so remember, we've talked about it before. The bigger the slope, the faster the speed. Okay, or the steeper the line, we've said in the past. So we have to look at which one is the biggest slope. So if you look at these cars, some of these are improper fractions. So if you think about the what the fraction represents, so that first one, 1/2 is 0.5. Okay, 4/3, if you divide on that your calculator, that's 1.3 repeating. 3/2 is 1.5. And then 5/4 is 1.25. And then this guy had a slope of 0. So all we have to do is look for the biggest number. So in this case, that slope that had the 1.5. So the equation that had the biggest slope, or the fastest car, was the car that had the equation y equals 3/2 x plus 1, because that 3/2 was the largest slope. All right, keeping in mind of that same car, the starting point of the car is going to be your y-intercept. Okay, so when we take a look at the part of the equation which represented where the car started, that is your y-intercept. Okay, or at 0, what was that number? And that's, remember, how we represent our y-intercept. How is that represented on the graph? Again, it's the y-intercept. So if we look at a graph and say it hits right here, there's our starting point when time was 0. That's how far it was from the start line. When we look at the table, well, we know that the y-intercept is always 0 comma some number, so we can find that y-intercept by looking by the number that's in that blank. And then part D says, which car has a starting place that's farthest from the starting line? So if we go back and we look at our equations, I'm going to circle our y-intercepts in this green. So there I had 10. Well, this one technically has a plus 0. Here I have 1. Here I have 17. And then 5. So clearly the biggest number is that 17. So the car that had the starting place farthest from the line was the y equals 17 car, because the y-intercept was the largest, or the biggest. Okay, so we've talked about domain and range. So one of the things to remember is that domain is the x values and range is our y values. Oops, that was supposed to be an arrow. So when we talk about domain, those were our x values, and those x values represented time. So if you think about time, okay, we can't really have a negative time, but you could have a time or a part where the car hadn't started moving yet, so a time of 0. So we know that our time has to be greater than or equal to 0. Okay, and that's going to be our domain. Our range was the distance the car had traveled. Okay, so again, we can't really go backwards. I mean, I guess the car could go backwards, but in this situation, none of our cars did go backwards. And we want that distance also to be 0 or higher. If you were starting on the starting line and the car wouldn't move, then its distance is 0. But anything beyond that, the distance would be 0 or higher. And then one of the things we talked about before was the difference between discrete and continuous. So if you remember, discrete was where you had a bunch of points on a line. Maybe they connected, maybe they didn't, but you could not necessarily connect them. We talked about shoe size. Remember, shoe size was discrete because you can have either a size 7, a size 7.5, an 8. There is no 8.1, 8.2. And then continuous is where there would be values in between. So if I was looking at something like time, where it was 1 minute, 2 minutes, 3 minutes, and I was looking at the distance the car was, well, I know that at 0 minutes, it might have started there, but at 1 second, it's going to be here, 2 seconds, 3 seconds, all the way up to a minute, it maybe goes there. So there are points in between. So in this case, all of these functions would be continuous because any amount of time has to be continuous, because you can go 0.1 second, 0.2 seconds, 0.3 seconds. Any amount of time can be written, I guess we can say, as small decimals. So like I said, 1 second, 1.1 second, 1.00001 second. There's a lot of different points in between those cars, so it's going to keep going forever, or be what we call continuous. All right, taking a look at the next page, we're going to skip question 5 and we're going to jump right to questions 6 and 7. And again, this was somewhat similar to what we were just talking about and what we did in section 28.1. It says each pair is a representation, or each pair of representations in items 6 and 7 describe functions of a traveling vehicle. Which vehicle is traveling faster? Okay, so we know that the faster the vehicle, right, the faster the speed, or faster the car, the bigger the slope. So we just have to figure out the slopes of each of those. And once we do that, we just look for the larger of the two numbers. So remember, when we have a graph, it's really important to find points that we can actually calculate. So I can see that I've got a point right there. And let's see, we don't have a point at 5. It does look like we have a point right here, maybe at 10 seconds. And those aren't the only 2 points. Those are just ones that I saw that were nicely, that I could find nicely. So if I find my slope, remember it's the change in y. So how far does it go up? It goes up from 5 to 10. So that's a positive 5. and then the change in x, which would be positive 10 or 10 seconds. So here our slope is 5 over 10, which we could reduce to a half. Okay, if we look at letter B, our slope, these are going up by 10. And then on this side, it's going up by 5. So if we find our slope there, remember it's the change in y, which in this case is 10 divided by 5, and 10 divided by 5 is 2. So all we have to do for this particular problem is look to see which one of these two slopes are largest. And obviously 2 has to be bigger than 1/2. All right, if we take a look at number 7, we're going to do the exact same thing. Except for the first part gives us words. It says the push car traveled 5 miles an hour. So we know that speed is our slope. Each hour it goes 5 miles, so it would go up 5 over 1, up 5 over 1 on the graph. And if we look at this particular graph, we've got to find the slope there. So if I go right there at 0, 0, and let's see if we can find a nice point. It looks like I've got a point right there. Over 5, up, that'd be 15. What would that be? About 8, what is it, 15? That doesn't really work too nicely. But it's going up a little less than 2, because if that was 17, that would be 19, that would be 20. So it's a little less than 2, but that's okay. If we go from 0 to, say, 19, that went up 19 and over 5. And if we take 19 over 5, that's a little bit less than 5. If we divide that in our calculator, what do we get? We get 4.8, which then is a little bit lower. So that means this slope right here is the higher of the two slopes. So A would be going a little bit faster. All right, so looking down at the bottom, it's going to talk about something we've already talked